Enabling scientific discovery is what the National Center for Supercomputing Applications is known for. One innovation under development is a collaborative software tool called the Biology Workbench. Researchers and medical doctors who use this new tool will be able to access vital information necessary in finding cures for a wide variety of diseases like Alzheimer's, cancer, and perhaps even AIDS.
It reduces the time taken for a biologist to access all this information and knowledge from days and months to minutes and hours.
Developed by Shankar Subramaniam and his research group at the University of Illinois at Urbana-Champaign, the Workbench gives researchers the power to search a wide variety of remote databases without any prior training. This is all done through a simple World Wide Web browser interface.
We decided that we should combine the power of the World Wide Web with the power of biological tools and databases so that there can be a seamless access of these tools for a bench biologist.
Here, a protein sequence is inputted, and the matching sequences can quickly be found. Within minutes, researchers can locate a three-dimensional representation of the molecule. Now, a medical doctor can easily use the same tools as a seasoned computational biologist.
We can think seriously now in terms of rationally understanding function, mechanism, and therefore target drug design.
When I first saw the Biology Workbench, it took me a little bit to realize that this is a radical departure from the way that we construct software, and that this is not about biology. This is about software engineering that could be applied to any discipline.
The Biology Workbench is an example of web-based computing. Using the World Wide Web to link one computer or database to another is a new paradigm in computing that literally provides global access to information.
So this is software that is appropriate for sort of a 21st century approach to global knowledge and global production. It's a radically different view than the old view of one piece of software, one machine.
Crumbs is a virtual reality application which involves volume rendering biological datasets in the cave. Developed at the National Center for Supercomputing Applications, Crumbs authors are investigating the use of audio to augment the visual interpretation of the data volume. The main task of Crumbs is to place markers along fibrous objects within a three-dimensional visualization. However, the dense nature of many biological datasets often impairs visibility for structures of interest. So the sonification process is a method to help researchers see into these dense volumes.
We knew we wanted to use sound to help the placement of markers in the data volume, but our experience in the past with some sound things are simple mappings between data value and frequency. It's very fatiguing to listen to and can become irritating over time. So we came up with the idea of trying to use melodies and having the melodies tied to the placement of markers, starting and ending cleanly without an abrupt start and abrupt end. And also, we wanted to have the melodies be a little less obtrusive, be in the background more. So we went to Robin Barger of NCSA's Audio Development Group to see if he could come up with a solution with these kind of criteria.
Sonification began as an exploration of the parameterization of sound, which means that we can create sound driven by data. What we're doing now is finding that, well, it's not just enough to control a few parameters by data. We really have to know perceptually and cognitively what the listener's experience is and organize the mapping of the data according to the perception and cognition. So what we've tried to do in the Crumbs process is to use a lot of parameters to characterize one data parameter. A lot of musical and sound synthesis parameters are focused to help someone hear one change in the data, which is a very macroscopic change. And those parameters are designed so that the sound has musical properties, musical syntax, and a kind of musical meaning for the listener. And from that musical meaning, the listener formulates the meaning that they're supposed to get from the data set.
Crumbs creates musical signals in the Baroque style, common to both classical and folk music. As a user probes the data, the number of instruments present varies with the data values. The voxel value of the marker's location is the information which controls the sounds produced.
This window is a simple slide bar which is intended to illustrate how the data value changes the sonification sounds. At the bottom of our data range, we have a single guitar very softly playing. As we increase the data value, the sound gets brighter and a piano joins. More into the middle, a synthesized sound comes in. And the piano comes in at a higher octave, along with a bassoon. At the very top of our range, we can hear the flute. Actually, we're very happy with this first implementation of the melodies that are trying to fit the criteria we laid out for our sonification. Some of the lessons we've learned from this is that you have to have the tempo of your music match the tempo of marking points. There's quite a bit of dead space between the notes and the melodies that we have, and so we're going to try and make that a more continuous sound. Another thing we'd like to change is we'd like to get off the special purpose hardware, which is synthesizing the sounds right now. Those are located in the cave. We can hear them fine in the cave. But we'd like to be able to run this program on a desktop.
Moving to the workstation environment with sound samples will make it a lot easier for the scientists to deal with, because they'll have everything that they need right in front of them to work with. And they will be able to program the samples into their application exactly the way that they want to, without having to know how to operate any external hardware devices.
The sonification in crumbs is a departure from pure data-driven sound schemes, and that musical expertise can play a significant role.
Sonification is a very young field, and a variety of directions are being pursued by researchers, some of whom are scientists, some of whom are psychologists, very few of whom are musicians. The result is that lots of mappings of data to sound are not really effective from a sound synthesis or musical point of view. You hear lots of changes, but you don't know what to make of those changes. We've tried to focus the notion of data mapping to sound in a way that makes sense musically, it makes sense cognitively and perceptually, and it communicates something very intelligible about a data set.
The first implementation of Caterpillar's distributed virtual prototyping system was recently completed at the National Center for Supercomputing Applications, housed at the Beckman Institute on the campus of the University of Illinois. Participants at 3 different locations saw and heard each other as an integrated part of a shared virtual environment while examining a Caterpillar vehicle design across high-speed networks.
Our system supports collaborative design review and interactive redesign. You can actually environment allowing natural communication and interaction. We think it's a major leap forward in technology, allowing geographically distributed design teams to effectively work together to bring Caterpillar products to market.
The objects are created from the same Pro-Engineer CAD designs used throughout the vehicle design process at Caterpillar. Dynasty, a dynamic simulation package currently in use at Caterpillar, allows the CAD designs to be driven and tested in real time. Any number of remotely located sites may join in the shared virtual environment.
Modifications on, or?
Hi, I see that you guys have met each other.
Oh, hi, Val.
Brian and Tim, go ahead and come over toward the wheel loader and we can have a talk about some of the work Brian's been doing.
There is no server to run and no master site. Participants join in using multicast over high-speed computer networks for peer-to-peer communications. Each site runs its own copy of the simulation software on the local computer, and changes to the vehicle or environment are multicast to the other participating sites, maintaining the synchronicity of the shared virtual environment.
So what we'd like to do is to move this access panel back and up a little bit so that we can get at the fuse box and everything without having to rotate the fender out.
So you're thinking of putting it like there somewhere, or?
Right, just moving it back and up a little bit.
Okay.
That's excellent.
Each site controls its own viewpoint. The video coming from each remote site is placed in the virtual environment at the corresponding site's viewpoint.
This technology, collaborative virtual prototyping, will be one piece of technology that we'll need to rapidly exchange product information amongst all of the individuals that have to make decisions about a project so that we can achieve a good design in the shortest amount of time, dramatically reducing the time to market for us.
Caterpillar's ongoing challenge is to compress product design cycle times while allowing engineers to quickly evaluate many alternative designs.
This is a tool that can bring together Caterpillar manufacturing personnel, marketing personnel, and design engineers to bring a better product to market, one which will meet or exceed the customer demands on the first try.
Current research is directed toward using Caterpillar's virtual prototyping system over ATM networks to enable high-quality interaction between Caterpillar engineers located in the U.S. and in Europe.
I'm Larry Jackson from the Software Development Division at NCSA. We've constructed a tool system called Habanero, which facilitates collaboration amongst people distributed throughout the internet using a wide variety of tools. This system communicates via a mechanism we've developed that uses the Java programming language from Sun. As such, it'll run on a very, very wide variety of hardware platforms and operating systems, allowing you and your colleagues to work together pretty much regardless of the nature of the hardware you actually own. The tools that we've constructed offer a variety of reasonably usable opportunities in their own right, but they also are typically provided in source code as well to enable people who are learning to construct tools of their own to be able to use this as a baseline code, a reference. The material that we'll show you today is several of the tools that we're already shipping, and we can, in principle, support just about any kind of additional tool that a person would need. Some of our projects are quite complex and will take perhaps the better part of a year to implement, but a general Java applet porting to Habanero can probably be done in well under a week. The Habanero system will support distributed work between teams of colleagues and also between teams that are made up where some of the members are particularly knowledgeable and are guiding the work of others. This could be, say, a teacher or a senior distinguished person, or even consulting scientists working with teams such as students, museum participants, visitors, and even staff, either in the design process, a guided education and discovery applications, or just staffs working together across distances. Again, the system will run on a wide variety of hardware, so it's not necessary to standardize on one particular vendor to accomplish your work. In the tool palette here, you can activate any of these different tools just by clicking on them. Once you've activated them, the tool comes up as is shown here. Selection of a tool from the tool palette causes this tool to be activated. This particular tool was created by the Department of Atmospheric Sciences at the University of Illinois, and it shows current weather conditions and a series of overlays. For example, the radar summary and the pressure isobars across the United States. In addition to that, it can also query down in the lower section and receive weather forecasts for any selected area. This red cross that we've created here allows you to move the selection point to a different location. In this case, I've moved it to Nebraska. We've received a new weather forecast set for Nebraska, and in the red stripe area, colleagues or students working remotely with you will see the motion of the shared pointer there, the red cross, onto the Nebraska area. In this example, we'll use our whiteboard system, which can allow you to open either a local file or open a file that you can retrieve anywhere from on the web. And I have these two computers hooked into a session together. We'll initiate a file load from the SGI, and the Pentium receives this file. In this case, it's an X-ray of a person's leg. We can take this system, annotate regions of interest using standard graphics tools that you come to expect, and go ahead and add text to it. For example, and each of these are done as independent objects. So if the material isn't exactly right, I can reposition it and it will show up on my colleague's screen. I can also delete things individually and they'll be removed from the colleague's material as well. The image that's being worked on can, as I said, can be derived either from your local machine or from some server. The important thing about using it from your local machine is you don't have to operate a server at all. You can be working directly with the scanner connected to your machine, a digital camera, or some other form of a data capture device, and sharing the material off with your colleagues. The Habanero system accomplishes the necessary serving of the information. The Habanero system communicates across the internet, and primarily using a protocol that we've developed that exchanges Java objects between different people's computers and the different tools. This is not necessarily tied in with the World Wide Web. It doesn't use exactly the same protocols, but we can use those, and tool authors can invoke the web from their tools. For example, the whiteboard allows loading of images using the HTTP protocol from any web server in the world. Although it's not directly tied to the web, we will also have a web browser that's a shareable tool and usable by several people coming in as release in the early part of the year. What this will allow people to do is to take teams of people and go do resource discovery, research projects involving material, the wide variety of material that's reachable via the web. There's another system also which provides essentially the converse, the tie of the web to the synchronous communication that Habanero facilitates. This system is called Joule, and it has, among other things, the capability that when you encounter a web page containing essentially a habanero icon, you can, by clicking that icon, launch a direct, immediate communication, synchronous communication with your colleagues, again, using the tool sets of your own constructing. The habanero system was designed to support teams of scientists that use the NCSA facilities from all over the country. As such, these different teams own all different kinds of hardware. They have operating system revisions that are basically everything you can buy. We've built the system to facilitate these teams sharing their work with their colleagues regardless of what the distance is, and to enable them, all the colleagues, to actually participate in the environment that their different tools create for them. They don't have to, say, make slides or presentations, get on airplanes and try to convince people remotely as work that has already occurred and its validity. What they can do is actually take people directly into the tool and show them and allow them to participate. In one recent example that we did, we can show you here, the system was constructed originally using the material from the cave, the 3D environment that NCSA has created, and in here on the left-hand portion we see a cave emulator which has a garden being collaboratively planted by several participants. You can see the cave operator's hand here holding an ear of corn. What we've created is a habanero likeness of this in 2 dimensions, and that potentially will use considerably less bandwidth and be runnable on the normal home hardware systems that people would own. In this case, you see a small icon character again holding this ear of corn. This equates to your colleague in the cave. The mouse cursor shows the position of the habanero user in the 2-dimensional overhead view. This egg-looking avatar represents the habanero user, and the person using the cave system sees the habanero participant hovering and flirting around the garden. Also, the habanero user can plant plants the same as the cave participant. Although this is a simplistic example for starters, showing the different state interactions of the different participants in the same virtual space, the extensibility to scientific tools is clear. For example, a cave rendition could have things such as electron molecular models and showing the electron clouds and the different contours related to that, whereas a user with limited hardware or limited bandwidth could be using, say, the stick figure-like models that were common in high school. But the molecule being modeled is the same. If one participant makes a change, it detaches a group and puts something else in its place, the other participants would see that detachment and the reassignment of the new material, although they'll see it with differing levels of fidelity depending on the quality of the hardware that they own. The habanero system communicates across the internet, and primarily using a protocol that we've developed that exchanges Java objects between different people's computers and the different tools. This is not necessarily tied in with the World Wide Web. It doesn't use exactly the same protocols, but we can use those, and tool authors can invoke the web from their tools. For example, the whiteboard allows loading of images using the HTTP protocol from any web server in the world. Although it's not directly tied to the web, we will also have a web browser that's a shareable tool and usable by several people coming in as a release in the early part of the year. What this will allow people to do is to take teams of people and go do resource discovery, research projects involving material, the wide variety of material that's reachable via the web. There's another system also which provides essentially the converse, the tie of the web to the synchronous communication that Habanero facilitates. This system is called Joule, and it has, among other things, the capability that when you encounter a web page containing essentially a Habanero icon, you can, by clicking that icon, launch a direct, immediate communication, synchronous communication with your colleagues, again, using the tool sets of your own constructing.
One of the primary features of Joule is that it integrates asynchronous tools such as the type where you would leave a message for a collaborator and that collaborator comes back and looks at it later, with synchronous tools such as Habanero, where you're having a real-time conversation, where you speak, I hear it right away. The Joule environment is based on people, places, and things. Up here in the right-hand corner, we have a list of teams that are being supported by this particular server. And I've selected the Joule development team because that's the one that has all the tools installed in it at the moment. You have a tools palette and you have a documents palette. The tools, both of the palettes are divided into rooms, so to speak, and you can put anything you want to into these rooms. For example, what we have right here is a water cooler. And if I click on the water cooler, what I'm actually doing is launching Habanero. So what I can do here is I can jump directly into a synchronous conversation with somebody else in this space. Other types of tools that are supported by the Joule environment can be database applications where you're pulling information about people out of a database, or things like Hypernews where you're having a threaded discussion. It's an asynchronous tool. I leave a note, somebody else reads it later, answers it, and so forth. In addition to the tools, you also have a document palette down here at the bottom. And to get to your documents, if you click on it, it comes up on the other side of the screen. And you can see all the stuff that's in this particular, all the objects that are in this particular room. For example, in the demo room, we have a file cabinet and a folder, and inside of the file cabinet, we have documents. And you can just click on the documents and see the contents of the document itself. There's also a bit of metadata here that will tell you about the document, who wrote it, when it was last updated, and so forth. Makes it a little bit easier to know whether or not you need to look at it. The way you might use this in a museum setting where you have children coming in as a field trip and sitting down in front of the computers is that you can have collaboration between different groups of this type. So you have one set of kids in one museum, another set of kids in another museum, and they can use the synchronous tools, such as the Habanero tools, to talk in real time. They could also post notes to one another using things like Hypernews. You've got calendaring in there so that you could leave messages for the next event that they can look at. And this is a workspace. The whole purpose of it is to do work. Another scenario might be one of your tools could be a simulation. The kids run the simulation. That simulation might go off and run on a supercomputer someplace that takes a little time to do. While the simulation is running, the kids are doing other things within the environment. Then when the simulation completes, the simulation code could send a notification message back to the environment and tell the kids, hey, your results are ready, and they're in container results set. Joule is a work environment. It provides a space for people to come to work or to play. You could use it in schools, museums, virtual communities, virtually anything where people are trying to work together towards some common goal.
Imagine climbing to the summit of Mount Everest, though confined to a wheelchair. Standing in the Nairobi desert in the year 3185. Holding the entire Library of Congress in the palm of your hand. If these ideas seem impossible, think what early settlers of our country might have said to exploring the woods with flashlights, or flying over the Continental Divide in an airplane. Who living then would have believed it possible to walk on the moon? Argonne National Laboratory supports a new community of scientists and researchers who are breaking barriers to even more revolutionary advancements. The barriers? Time and distance. The barrier-shattering prototype, iWay.
All right, you want to read it back to me?
iWay, which stands for Information Wide Area Year, began as an idea to push the limits of high-speed distributed computing. Using telecommunication carriers to connect remote supercomputers, iWay demonstrated a nationwide collaborative environment. Virtual reality interfaces, like the Cave, meant scientists and researchers could literally immerse themselves in data.
What we were proposing to them is to take a leap forward about 10 years. Seeing where things break and where they hold up, that's of critical importance and value to the carrier community today.
iWay won the support of independent telecommunication carriers and some 30 different research and academic institutions. Overcoming time and distance, iWay debuted its Supercomputing 95 in San Diego, California.
What they're seeing is networks at speeds that they've never seen before and probably will never see again for another few years.
We did definitely push the envelope. There's a whole community of people now who have a different way of thinking about how to do supercomputing, how to do visualization, and have been part of an experience that will guide or influence how they think about science in the next few years.
One problem was finding a way to let many different kinds of supercomputers talk to each other. Led by Argonne, iWay teams developed iPop machines, point-of-presence computers, installed as uniformly configured gateways to the supercomputers.
We're going to go with Argonne.
The use of these iPop machines meant that we could basically develop a single set of software that would run at all the sites.
iWay teams wrote iSoft, management and parallel programming software, which created a necessary standard software operating environment.
We had a small team of people at Argonne National Lab who defined the basic architecture.
iWay enabled new ways to conduct research. Virtual reality interfaces allowed scientists to interact, come face-to-face with their data.
This year we're introducing two more virtual reality projection-based devices. The Immersidesk, which is a single-user drafting table format device, and the NII Wall, which is a very large screen projection display which can be in stereo or mono mode.
One of the reasons, of course, we've been working on the virtual reality is because it's an excellent test for this kind of technology. We need the supercomputers to give us the realism in the simulations, and we also need the high-speed networks to give us the feel of telepresence, of being somewhere else.
From inside the cave, this simulation shows gas collapsing to form stars. Supercomputers and high-speed virtual reality environments like this one are critical to further develop interpretive models of underlying physics. In this tornado simulation, the Powerwall enables scientific discovery by locating areas within the storm that have differing flow characteristics. The immersive capabilities supported by virtual environments permit engineers to go inside this virtual boiler and understand flue gas flows.
We had been looking at issues of how to pull high-performance networking and high-performance computing together. So when the iWay project came along, it was somewhat of a natural fitting into an experiment.
We really merged a lot of communities. So we brought together the advanced networking community, we brought together the parallel computing community, the applications community, and the virtual reality community. And we also explored how to manage this large endeavor. I mean, we've had over 300 people involved in making the iWay work.
The first distributed supercomputer network of its kind, iWay presented many unknowns to network specialists. Managing its fragile and complex character from the Network Operations Center meant solving round-the-clock problems no one had ever seen before.
There was nobody coming down here saying, "Are you doing your job?" I think it was that we just all wanted it to work.
In another significant accomplishment, Argonne, working with IBM, staged the first live press conference ever to be run over ATM links. Using a digital video server, the press conference was held between scientists and engineers in San Diego and news reporters in New York City. iWay's success is just the beginning of understanding the technology it represents. Perhaps for the first time, we are witnessing capabilities and resources accelerated beyond our ideas. Perhaps for the first time, we will find ourselves only limited by what we can imagine.
I think that there's a lot of national support for continuing something like the iWay to provide a test bed where people can actually understand how to use this capability.
There's a great team here, both from San Diego, from Oregon.
We've had a lot of student volunteers. We had maybe 8-10 rooms that we had to have workstations and cameras in every day.
We've learnt that a lot of the things we thought were hard were even harder than we thought. We learnt that other things that we thought were hard were perhaps not as difficult as we might have imagined. And we also learnt about problems that we hadn't even thought of.
We figured out that we were probably trying things that was about 3 years before it'll be generally possible to do it. If we tried to do this last year, nothing would work. If we do it 3 years from now, it would be uninteresting.
What iWay has done on multiple levels is touched various communities that will be impacted by the research, by the networking experience, and by the impact of those two combined on the way we do business, on the way we educate, on the way we basically communicate.
New use, so it's exciting stuff.
I got outside today for an hour to go buy earrings for my daughter. That was it.
At this point, we're calling it a huge success, and we learned a lot.
At this point, we had never had to pull all of our ATM customers into a single facility. It was a challenge.
What we actually did accomplish was much more than we ever expected that we'd be able to do.
I don't know where the other gun is. Live action video. We must de-stress these people every now and then.
So how was the show, Bill?
Yeah, the show's great.
Hi, I'm here to tell you about Calvin. Calvin is a virtual reality design environment that uses a concept of heterogeneous perspectives, allowing us to investigate issues in providing technology to support collaborative VR over high-speed networks. These include providing representations for virtual co-presence, video and audio teleconferencing, virtual VR interfaces, and database technology for sustaining persistence in virtual worlds. This use of heterogeneous perspectives allows each participant to tailor the world's representation to their specific needs based on their role in the collaboration. Calvin runs in the Cave Virtual Reality Theater. Each participant dons a computer-generated avatar body to establish a presence in the virtual environment. Tracking the location and orientation of the user's head and hand allows the system to transmit gestures, such as nodding or pointing. These avatars provide significantly contrasting representations and give sufficient cues to determine where the avatar is facing, allowing the participants to communicate notions of relative position, such as, "It is to your left." Some participants take the role of mortals, who see the design as it appears life-size from within. Mortals are better at fine manipulation and seeing details of the environment. Other participants take the role of deities, who see the design in miniature from the outside, and hence are better at gross manipulation and seeing the overall picture. Mortals and deities may also take on heterogeneous roles in the environment and have heterogeneous abilities. The deity may take on the role of a teacher or tour guide, while the mortal takes on the role of a student or client. Here we see a participant in the cave taking the role of a mortal. High above, the avatar of a deity can be seen. The deity is portrayed by another user sharing the space from an immersidesk. Calvin's network component connects several distributed Calvins running on heterogeneous VR platforms to a central data store. This data store maintains information on the current design as well as past designs. Users in the cave can move the cave through the virtual environment or walk about the cave. The environment automatically adjusts the height of the floor, allowing the user to walk on objects in the scene. Each participant manipulates objects using the wand. Here you can see a cave user moving an object in the space. Calvin has two complementary user interfaces, the virtual visor and speech recognition. The virtual visor simulates a head-up display, allowing the user to choose a menu option by gazing at it. Here you can see a cave user bringing up the menu and turning video teleconferencing on. Speech recognition allows the user to bypass the visor menu through voice commands. Here you can see an Immersidesk user talking to Calvin.
Calvin, video on.
Enhanced video, active.
Participants in the design can communicate with each other using both audio and video, which are streamed over a high-speed ATM connection. Calvin has been used in the design of several spaces. The Powerwall room at NCSA, the GII testbed rooms at Supercomputing 95, and the ARPA integration testbed prototype. Calvin is currently being used in collaboration with local industry to provide techniques for prototyping in VR. We are also applying the techniques derived from Calvin to two new projects: a narrative educational environment based on constructionism called NICE, and visualizing scientific data through heterogeneous perspectives.